Hi everyone, this is Mrs. J, and today we're going to learn about the product and quotient rules. I have a quick warm-up for you guys, so please pause the video and hit play when you're ready to check your answer. Alright, go ahead and check your work here. So if we want to find the equation of the tangent line, we can use the derivative, so f prime of x, to find the slope of our tangent line. Remember, the derivative of e to the x is just e to the x. And then here we can use the power rule to find the derivative of x, which is just 1. So f prime of 0 will equal 3, and that's the slope of our tangent line. This point 0, 2 is a y-intercept, so the slope, or the equation of the tangent line would be y equals 3x plus 2. All right, so today we're going to learn two more rules for differentiation. The first is the product rule, and the second is the quotient rule. So for the product rule, it says if f of x and g of x are both differentiable functions, then you can find the derivative of the product of f of x and g of x by taking the product of f of x and the derivative of g of x plus g of x times the product of f of x. So f of x times g prime of x plus g of x times f prime of x. So first times derivative of second plus second times derivative of the first. So this is a way that, again, we can find the derivative of the product of two differentiable functions. All right, so before we start using our product rule, we're first going to prove it. And to prove this derivative, we're going to actually use that limit definition. So here, here's the derivative we're proving. So we have the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. So to evaluate this limit, I'm actually going to do something that's maybe not super intuitive, but I'm going to try to create a scenario where I can factor by grouping in the numerator. So I'm actually going to add and subtract out the same term that will allow me to do this without changing anything in our numerator. So I'm going to actually kind of steal a portion from our first term. I'm going to take the f of x plus h. I'm also going to take a portion of our second term, which will allow me to factor by grouping. So here we have f of x plus h times g of x plus h, and then here's kind of that tricky step. I'm going to subtract away this term, f of x plus h times g of x. Again, a portion from the first term and a portion from our second term. But since I subtracted it, I have to add the same thing to maintain the same value in our numerator. And then we still have minus f of x times g of x. So kind of a, again, not a super intuitive step, but here you can see I didn't change the value in our numerator, and I've created a scenario where I can try to factor by grouping to allow us to evaluate this limit. So if I group our first two terms here, you can see that I can factor out f of x plus h, and that leaves us with g of x plus h minus g of x. And then from our second two terms, I can factor out g of x. And then I have f of x plus h minus f of x. And then all of this is over h. So at this point, maybe you're noticing something kind of familiar in our numerator, but just to make it a little bit more clear, I'm going to rewrite this. I'm going to kind of separate this into two separate fractions. So f of x plus h times g of x plus h minus g of x all over h plus g of x times f of x plus h minus f of x all over h. Again, I just split up the numerator into two separate fractions, and now I'm actually going to look at within each fraction individually. So here you might actually notice that when we have this g of x plus h minus g of x all over h, this is actually the limit definition of g prime of x. So this is the derivative of g of x. And then if I evaluate this limit using direct substitution, we know that h will go to 0, and what I'm left with is just f of x. So now I'm actually evaluating our limit. So again, this portion just becomes f of x, and again, this is the definition of g prime of x. And then if you go to evaluate this portion of our limit, you'll notice here that this f of x plus h minus f of x all over h, this is the definition of f prime of x. So what I have left in this portion is g of x times f prime of x. So I'm just replacing this with f prime of x, and if I do direct substitution with this limit, this still stays g of x. And then after I've done that, you can see that we actually have that product rule, f of x times g prime of x plus g of x times f prime of x. So now we have proven our product rule. All right, so let's give one a try together. So here we have the function y equals e to the x times x plus 5 plus 1 over x. So we can consider this to be our first function, e to the x, and we consider this to be our second function, x plus 5 plus 1 over x, and let's use our product rule. So y prime will be our first function times the derivative of the second. So the derivative of x is 1, the derivative of 5 is 0, and the derivative of 1 over x, if you treat this as x to the negative 1, be negative x to the power of negative 2. So we can write that as minus 1 over x squared. And then we do plus the second function, so x plus 5 plus 1 over x, times the derivative of the first. And remember, the derivative of e to the x is just e to the x. So again, first times derivative of second plus second times derivative of first. And from here, we'll just try to simplify as much as we can. So you'll notice that both of these expressions or polynomials are being multiplied by e to the x. So we can do e to the x times 1 minus 1 over x squared plus x plus 5 plus 1 over x. And then this we can just combine like terms. So we can write our final answer as e to the x times x plus 1 over x, minus 1 over x squared, and then plus 6. And we can leave our derivative like this, rather than, you don't have to distribute the e to the x. But again, we were able to find this derivative by considering each of these separate functions and then using our product rule. All right, let's try another one together. So here we could consider this to be our first function, and we could consider this to be our second function. And we could use the product rule to find this derivative. So again, first function times the derivative of our second. So we'll do the product rule here. So 4x cubed plus 1. And then second function times the derivative of our first. So again, we'll use that product rule and we get just 2x. And then from here, it's really just a matter of simplifying as much as we can. So we can multiply this out. Oops. 12x cubed plus 3. And then here we have plus 2x to the 5th plus 2x squared minus 2x. And then we'll just combine like terms. So here we have 6x to the 5th plus 12x cubed plus 3x squared minus 2x plus 3. And that is our derivative. I do want to point out that you also could have just multiplied out these polynomials from the get-go and then just found that derivative using the power rule. So you don't actually have to use the product rule to find this derivative, but I think it's probably a little bit quicker, or it might save you a little bit of time, but it might actually be faster to do it just with the power rule after multiplying it out. You would end up with the same exact answer. All right, so now we're going to talk about our second rule for today, which is the quotient rule. So again, we have f of x and g of x are both differentiable functions. Then you can find the derivative of the quotient of those two functions using this rule. So g of x times f prime of x minus f of x times g prime of x all over g of x squared. So there's like a little trick that we can use to remember this. It's low d high minus high d low all over low squared. So again, by low, we mean the function in the denominator. So low times the derivative of high, which is the numerator, minus high, so numerator times d low, the derivative of the denominator, all over the denominator function squared. So again, low d high minus high d low, all over low squared. And you can find a proof of this in our textbook. The process is kind of similar to the product rule, but I'll let you guys find that one on your own if you are interested. Okay, let's give this one a try together. So we're going to call this e to the x are high and 1 plus x is low. And we can find this derivative using our quotient rule. So remember, we do low d high, and the derivative of e to the x is e to the x, minus high d low, and the derivative of 1 plus x is just 1, all over low squared. So notice it's not the derivative of our low squared, it's just our denominator, the function in the denominator squared. And then from here, it's just a matter of trying to simplify as much as we can. So here we have e to the x plus x, e to the x minus e to the x, all over 1 plus x squared. So we can see that our derivative is x e to the x, all over 1 plus x squared. And there you have it. All right, let's try one more together. So here, let's treat x cubed minus 1 as our numerator function, and then x to the fourth plus 5x is our denominator function. So we'll use our quotient rule again. So we have low d high, so 3x squared, minus high d low, so 4x cubed plus 5, all over low squared. And then again from here, it is just a matter of multiplying everything out. So that leaves us with y prime equals 3x to the 6 plus 15x cubed minus, and then just be careful with your grouping here, 4x to the 6 plus 5x cubed minus 4x cubed minus 5. And here we could try factoring out an x, and then we have x cubed plus 5, and all of that is squared. So we have y prime equals 3x to the 6 plus 15x cubed minus 4x to the 6. We have minus x cubed plus 5 all over x squared times x cubed plus 5 squared. Let's combine like terms. So we have negative x to the 6 plus 14x cubed plus 5 all over x squared times x cubed plus 5 squared. So in our numerator, we could factor out the negative, and we could try to factor the remaining polynomial, but in this case, it is not factorable. So this would be our final answer. All right, let's try one more together. So here, our function in the numerator would be square root of x minus 1. Our function in the denominator is square root of x plus 1, and we can use our quotient rule for this. I do want to remind you that we want to think of square root of x as x to the 1/2, just to make it a little bit easier for us to use our power rule. So for our derivative, again, it's low d high, so the derivative of this is actually 1/2, and then it's x to the negative 1/2, so over square root of x, and then minus high d low, which is the same, 1 over 2 root x, and again we just use the power rule for both of those, all over low squared. Then from here, let's just try to simplify. So in our numerator, both binomials are multiplied by the same term, so we can rewrite this as 1 over 2 root x times square root of x plus 1 minus square root of x plus 1. So here I'm just distributing this negative. all over square root of x plus 1 squared. And then we can cancel these terms out. And what we have left is y prime equals 1 over 2 root x times 2 over square root of x plus 1 squared. Here, this simplifies out, and then we'll move this down to our denominator, and our derivative becomes 1 over square root of x times the square root of x plus 1 squared. And this will be our final answer. All right, so I have 2 for you to try on your own. So go ahead and pause the video and give them a shot. All right, go ahead and check your work here. So you can see for part A, I used the quotient rule, and for part B, I used the product rule. So last thing we're going to talk about is some other applications of our derivative rules. So we're going to see how we can actually use our derivative rules to help us find different derivatives given different pieces of information about the function. So here we actually don't know what the functions are, but we have information about f of x and g of x. So here we are told that f of 3 equals 4, g of 3 equals 2, f prime of 3 equals negative 6, and g prime of 3 equals 5. So first we want to find f plus g prime of 3. So we know using our derivative rules from previous lesson that we can find the derivative of a sum by finding the sum of the individual derivatives. So this is simply just going to be f prime of 3 plus g prime of 3. So that's one of our derivative rules, and those are two things that we are given. We know that f prime of 3 is negative 6, g prime of 3 is 5, so we know that the derivative of this sum would just equal negative 1. So let's look at this next one. So here we have f times g prime of 3. So here we have the derivative of a product, so we can use our product rule to find this. So remember, for the product rule, it's the first derivative, or first function times derivative of the second, plus the second function times the derivative of the first. And all of these things are values that were given to us in the problem. So f of 3 is 4, g prime of 3 is 5, and g of 3 is 2, and f prime of 3 is negative 6. So we have 20 minus 12, which is just 8. And last we have f over g prime of 3. So here we have a quotient, the derivative of a quotient. So let's use our quotient rule. So remember, we have low, so we'll do g of 3 times the derivative of high, minus high d low, all over low squared. And then we just need to substitute the values we know. So 2 times negative 6 minus 4 times 5 all over 2 squared. So that gives us negative 12 minus 20 over 4. So negative 32 over 4, which is negative 8. So we can see that we can still use our derivative rules to help us evaluate limits, even if we don't, evaluate derivatives, even if we don't actually know the function, as long as we have the right information about those functions. All right, so that is all for today's video. Thank you so much for watching.